Welcome back, physics students. Today we are going to talk about fluids in motion. The opening slide we have here is, I know a number of you guys have done this. If you start up a garden hose, the pressure just comes out nice and slow and steady. But if you take your thumb and you cover the end of the hose, you make that opening smaller, it's going to really increase the viscosity of the water and it's able to kind of shoot it out like this. We're going to learn about why it does that and how we can calculate the new speed. Then we're going to learn about Bernoulli's principle, and we're going to learn about some other properties of fluids that attain to a fluid. So let's start out by looking at what is happening when we are increasing the speed of the fluid. Kind of goes to this idea right here. You have a big opening, okay? So you got a cross-sectional area of a hose. The water can flow through it nice and steady at a velocity 1. If you close down that opening, okay, well, this water, all of this water, is still moving through it, and it's not going to stop. So what happens is the cross-sectional area got smaller, so in order for all of this water to get through this opening, it has to go through a lot quicker. That's kind of the basics behind it. We have a formula that helps us calculate this. It's the cross-sectional area 1 times velocity 1, so it'd be like this part of it, equals cross-sectional area 2 times V2. It's actually pretty easy to calculate the new velocity of the water. Plumbers would use this because they'd have to know if they adjust the pipes in a house, like how fast the water is going to be moving. So this is definitely something, if you're thinking about becoming a plumber, this is something you would have to do. Oop, I have to change the iPad. Let's see here, like that. Alright. So we are back. So let's look at a problem using this whole idea. So it says water flows through a 9.6 diameter fire hose with a speed of 1.3 meters per second. Okay, so this diameter 9.6, the speed is 1.3. At the end of the hose, the water flows out through a nozzle whose diameter is 2.5 centimeters. So the new diameter is 2.5 centimeters. What is the speed of the water coming out of the nozzle? All right, so to solve this one, it's pretty easy. We're going to go area 1 times V1 equals area 2 times V2. This is going to be the velocity 1. Now, the diameter is in centimeters, so we're not just going to use 9.6 because we need the area. But the diameter, we know it's 9.6. However, speed is going to be in meters per second. So we need our centimeters to be in a meter. So it's going to be 0.096. This is for meters. This one will be 0.025 meters. Okay, we have that to work with. But we should calculate the cross-sectional area. You guys know the area of a circle is pi r squared. We're given the diameter, so we should take the diameter, divide that by 2. So the radius of this one is 0.048 meters. The other one is going to be, so r for radius, 0.0125 meters. Okay, now we have the radius. Now we might as well just calculate the area, which is just pi r squared. So area, I'll call this area 2. Over here we'll call area 1. So area 1 would be 0.048 squared times 7 pi. So this area is 0.0072238. I'm just going to carry a couple digits there. The other area squared is going to be 0.00049, I'll call it 1. All right, so now we have our areas, and we know the velocity of the first section, so now we can calculate V2. All right, so V2 is going to equal, let me divide this side. So there's our formula. The area 1, 0.00, only need 1 0 there, 7238, so that's the area, times that first velocity, which is 1.3, divided by the second area, which is 0.0000, and that's going to be 491. All right, so we plug this into our calculator. 7238 times 1.3, divide that by 0.000011, and I get a velocity equal to, we'll use 2 sig figs, so 190 meters per second. That is coming out of the other end pretty fast, but it should make sense because it's going from a 9.6 down to a 2.5, and this speed is 1.3. Let's see here. I'm gonna double check this though. That number seems a little high. So let's go through there. I'm gonna double check the areas. Just seems like it's a little bit too much. Let's just see. So 0.096 squared times pi. Okay. So that's what's going on here. All right, so scratch that. Restart. Let's hit the restart here. 0.048 squared times pi. Or no, that's the right answer. 0.00723. Okay. Let's check the other one here. So we're gonna have 0.0125 pi r squared times alpha pi. No, that number's right. So we have our velocity is just gonna be 190. That's just what it's gonna be. All right. Just one. It's always a good idea to double check. All right. So here's kind of a follow-up problem where it says what nozzle diameter would be required to give the water a speed of 21 meters per second. So with this one, we're actually looking for the diameter, which would be right here. We know the V1, that's going to be 1.3. The area of this one is going to be 9.6. We did this one in the last problem. Move a decimal point over. So let's do that again. By 2, so pi r squared times second pi. All right, so then the area 1 equals, like the previous problem, 0.00723. All right, and we know that we want the speed, the new V2, to be 21 meters per second. So we eventually need to calculate the second area. So let's use that formula to figure that out. So we got A1 V1 equals A2 V2. The first area, 0.00723 times the first velocity, which is 1.3, equals, let's find what A2 is. We know the velocity is supposed to be, this new one is 21. So we'll solve that for A2. Times 0.3 equals that, divided by 21. So then the new area is supposed to be 0.000169. That's the area. The question isn't asking us the new area, it's asking us for the diameter. So what we need to do is use the pi r squared formula to get the radius. Then once we know the radius, we just have to double it. So we can set this equal to pi r squared. Let's solve that for r. So divide that by second pi equals that. Okay, and then second square root, second answer. So then the radius equals 0.00733. But again, the problem's not asking for radius, it's asking for diameter. So I got to multiply that answer by 2. So then multiply this by 2. So then the diameter ends up being 0.01, and when with sig figs, 2 sig figs, so 1.5 meters. So it'll be 0.015 meters, which would convert to 1.5 centimeters, which does make sense. So again, so when we're going from a different size cross-sectional area to a little bit smaller size, it's pretty easy to calculate. It's just A1 B1 equals A2 B2. Just use your algebra. You guys know how to do this. It's not hard. Let's see here. I'll skip this one. I'll leave that one for you guys. All right. So now we're going to talk about Bernoulli's principle, which is kind of a fun thing to talk about. I'm going to grab a piece of paper. So with Bernoulli's principle, it states that as the speed of the fluid increases, the pressure within the fluid decreases. So we have air pressure all around us. So if you actually take a piece of paper, you could try this at home. And I'm actually going to purposely kind of blow across the top of the piece of paper. Hypothetically, you might think, oh, it's just going to go down. But when you do this, it actually rises up. And you might be wondering, well, why is that rising up? Well, it's according to this. So Bernoulli's principle, as the speed of the fluid increases, the pressure within it decreases. So when you are increasing the speed of the fluid over the top, you're generating an area of low pressure. Okay, but there's still air pressure all around us. So we actually have an area of high pressure below the paper, which then causes it to rise up. So it is as simple as that. Now we call that lift in physics here. So that'd be a vocab when it's actually lifting up. So Bernoulli's principle, kind of a fun thing to think about. There's a lot of different applications for it. If you think about wings on an airplane, think about the design of a wing. They kind of have it designed, engineers do, so that it goes quicker over the top than it does here. So then what does the wing want to do? It wants to raise up. When we design roofs for houses, it's kind of the same thing. Is you don't want the whole roof of the house being lifted off and flying away. Now, the spoiler on a car is shaped in the reverse. So then therefore, like those really fast speed racers, they put them in reverse so that way it actually pushes down on the car and gives them more traction. So that's Bernoulli's principle. So here's kind of a fun concept question for you. We have this, let's just call it a Jeep, looks like maybe even a Ford Bronco. So what happens when the vehicle is moving down the road at a high speed? Is it going to cave in, like the top? Is it going to kind of stay the same? Or is it going to want to tend to kind of bow out? Now let you think about that. And actually the answer is it almost feels like the roof wants to get blown off. So it would be this guy right here. When I was in high school, I had a Jeep Wrangler, and yeah, and I had a soft top like this, and that's exactly what would happen. You'd get going down the highway, and it would just poof up. That's because there's an area of low pressure right here, and there's still air pressure inside the vehicle, so it just wants to get pushed up. All right, so we got a couple more vocab words we're going to talk about in this section. One is viscosity, and the other one is surface tension. So let's talk about viscosity. It's as simple as it's how much does a fluid resist flowing. That's basically all it is. If you pour it from one container to another, does it pour out kind of slowly? Does it pour out relatively quickly? So if you have corn syrup versus water, water pours out of the container pretty easily. The corn syrup's kind of slow and stuff like that. So your high viscosity resists the flow. So this would be like your corn syrup. So corn syrup has a high viscosity. It's resisting the flow. Something like water and even the air we breathe has a low viscosity. It does not resist a whole lot to flow. All right, and then the last thing we're going to talk about is surface tension. This is basically where water has all those hydrogen bonds, which you learned about in chemistry, and it creates kind of like a layer at the top, which some water bugs can float on.